All right. Last lecture, we looked at some of the Stern-Gerlach measurements we've been discussing and thought about them in terms of state vectors, um, as well as the postulate 4 from the textbook, which states that the probability of measuring a spin 1/2 system as either spin up or spin down is equal to just the projection onto that spinner up or down state of our generalized state vector squared. And we looked at those two things, and what we ended up showing was that we actually looked at measurements in the x direction and saw that a spin up in the x direction could be written as a linear combination of the spin up and spin down in the z direction states, and likewise the spin down in the x direction could be written as a linear combination of those spin up and down in the z direction states, but with a different relative phase. And we called these two states, we said that they were superposition states of these Z states. And today what we're going to discuss is sort of a little bit more detail on what a superposition state is and sort of what do they mean. And the way I like to think about superposition states versus what we would call a mixed state boils down to what do we actually know about that state. So let's think of this in terms of those Stern-Gerlach measurements, right? And let's say we have some beam of particles that we've prepared into some state psi. And we throw that into a Stern-Gerlach measurement apparatus aligned in the z direction. So we have our spin up and our spin down. And what would these two measurement results be? Well, let's say we've taken that beam of particles and we've prepared it into a spin up in the x direction state, which you'll recall is equal to the spin up plus spin down in the z direction over root 2. So this is one of those superposition states. If we take this, what we're going to end up with is 50% of our particles are measured as spin up, 50% of our particles are measured as spin down. Now, if we take that, do the same measurement, but we had, say, what we would call a mixed state, which really is just a beam of particles where, say, 50% of them are in the spin up and 50% of them are in the spin down state. If we were to measure that beam of particles, we'd get the exact same thing. 50% of them would be up, 50% of them would be down. So the results would be the same, but they'd be those results for very different reasons. In the superposition case, there's no missing information. They're not probabilistic because we don't know what's actually happening in the system. We know the state of every particle going into that Stern-Gerlach analyzer, but it is a mixture of these two Z basis states, the up and the down, and that measurement turns out to be totally random. It's not deterministic. It's a probabilistic measurement, but not due to any missing information. Whereas in this mixed state, where half the particles are up, half the particles are down, and it's just sort of randomly mixed in there, we get 50-50 because we don't know what each particle is going to be or anything. And that's the core sort of difference between those two. Now, you might be asking, okay, well, who cares? If they both produce the same results, why do we care about the distinction between the two? And to put it shortly, this isn't the only thing that we can do to a set of particles. It turns out that evolution in time, how these things are going to evolve, would be very different from these two states, and other measurements would have very different results. And the easiest one to show is, let's take that same beam of particles, right? Fire that beam into our Stern-Gerlach analyzer, but this time align it in X, and what do we get, right? Well, in this case, if we fired this beam into it, we would get 100% of our particles are spin up in the X case, because that's what every beam went in, and 0% would be in the spin down state because there's no spin down there. If we take our mixed state and put it in there, we'd still get this 50% up and 50% down measurement results. So again, very different measurement from these two states, one being in a superposition, one being in just a general mixed state. We could also do the same sort of thing with if we had prepared this into, say, a spin down state. We would just switch these two numbers and get 100% of them would have been measured down. So there we have it. The superposition states are essentially states that are written as linear combinations of our basis, or linear combinations of the basis states that we're talking about. In this case we just did, A and B were both had finite values, so there was contributions from both our basis states. Now, there is a little subtlety here that means it kind of depends on what basis we're describing our system in. So last class we discussed, we got to the point where our spin up in the x direction was a superposition of our spin up and down in the z direction. And we also showed that the spin down in the x direction was a superposition of those spin up and spin down in the z direction. But I mentioned very briefly that these two states also form a basis. So I could equivalently describe any general state vector as, I'll use different coefficients here, a linear combination of my two vectors in the x direction. And these span the space. So any vector in our Hilbert space could equivalently be described as this, which means if I'm describing, say, the state that we were just looking at, if I describe the spin up in the x direction, so let's say I have my generalized state and it's written, and I've prepared it into a spin up in the x direction state. Clearly, if I write it in this basis, that would mean that my c is equal to 1, and this isn't a superposition in that basis. However, if I take that same state and describe it in the z basis up here, I have that 1 over root 2 plus minus vector, and it is a superposition of those two z bases. So you can have the same state be a superposition state in one basis and not in the other. But in general, what we're going to call superposition states are essentially any state that is written as a linear combination of other states. So in our spin 1/2 system, some combination of these two where both A and B are finite. So there is contributions from both. And we'll generally, if we're talking about in this course, we're going to be sticking to superposition states. Very rarely will we actually be describing mixed states.